Okay, the recording has started. Class has begun. Let's get on to the the answers to the last quiz there. Okay. All right. So if I asked you the question, what is 2 plus 2, I can understand why you would answer 4. When your math teacher says, what is 2 plus 2, your math teacher is talking about the number 2, which is a scalar. And pure numbers by themselves, they are scalars. So it is in fact true that if your math teacher says what is 2 plus 2, it's 4. But notice I've got the question reworded a little bit here. If I tell you that I've got 2 things, and I don't tell you what those things are, okay? And I say the value or the magnitude, which is a word you need to get used to. If I tell you the magnitude of one of them is 2 and then the magnitude of the other one is also 2, and if I ask you what is the sum of those 2 things, in essence, I'm asking you what is 2 plus 2, but I'm doing it in a tricky way, okay? So 2 plus 2 does not necessarily equal 4 if the things that I'm dealing with are vectors, okay? So we are going to be talking a lot about vectors in this class, so get used to it. Okay. All right. So what is a vector? Well, it's something where in order to completely describe what it is, not only do you have to tell what the value of it is or the magnitude, okay, the number part, not only do you have to tell the magnitude, but you also have to tell what direction it's pointing. Okay, and forces are the best example of vectors. If I just say that I'm pushing on some object with 2 newtons of force, I have not told you everything you need to know. I also need to tell you what direction I'm pushing in, because it makes all the difference in the world if I try to add my force with somebody else's force and we're not pushing in the same direction. It just makes all the difference in the world. Okay, so make sure you guys know what vectors are. All right, so a scalar is the opposite of that. A scalar is something that doesn't have direction. Time is a good example of that. Mass is a good example of that. If I say that my body mass is, 120 kilograms or whatever it is, it doesn't make sense to say 120 kilograms to the north or to the south. It's just 120 kilograms. Okay, so things like that, those are scalars. Okay. All right. Now here is one of the questions on the quiz. I purposely didn't put the star in this one yet. Can somebody tell me what you think the answer is? I'll give you a minute. And hopefully, oh, by the way, guys, you should get in the habit of always having a calculator by your side when you hold class here. We're going to need it. Okay, so I'm seeing 2 different answers. So I need to see a couple more. Okay, so I'm seeing 3 answers, 4 answers, and 3 of them. Okay, looks like everybody's pretty much agreed except for one person. And then the other person's saying, wait a minute. Okay, so you guys are saying it's 42 foot-pounds, okay? And that is what I got as well. Okay, so make sure you know that. So 18 inches, that's 1.5 feet, because 12 inches in a foot. This crazy imperial system that we use, wouldn't it be a whole lot nicer if we used the metric system? Oh, so much easier. Like how many feet are in a mile? 5,280? Where'd they get that crazy number from? But how many centimeters are in a meter? 100. How many meters are in a kilometer? 1,000. Isn't that a much, much better way to do things? The answer to that question is yes, it is. Okay, meters if fun. Oh, is fun. Yeah, meters is fun, right. Okay, so it looks like most of you guys got good on that. The secret word was, of course, slump. The imperial system looks better. Okay. All right. So now your homework was simply to read the pages that I gave you in the chapter, in the book. You didn't have to read the whole chapter. And I asked you guys to make a list of anything that you might have found in there that didn't make sense to you. Okay. So let me pause and just give you guys a chance to ask questions. Did any of you come across anything in the reading that you didn't fully understand? And Luke, I agree, base 12 would be better than base 10, but well, in some regards. Okay. But anyway, 10 is what we got, and 10 works. Okay, but how about the questions from the book? Nobody has any questions from the book? Now that's either a very good sign or a very bad sign. Okay. And usually it's the latter, not the former. Usually what it tells me is that people didn't actually do the reading. Okay, so you don't have questions for me? Okay, well then I have questions for you, right? So there was a place in the book where they said there is no such thing as energy. You guys hopefully remember reading that. Did anybody look at that and scratch their head and said, what in the world are they talking about? Okay, wait, what do they mean when they say there's no such thing as energy? That's crazy. Anybody want to chime in on what? So when you read that, hopefully you said, well, that doesn't make sense. Anybody have any comments on that? I'm going to sit here until somebody types something. We might be here a long time. So do you guys believe that? Okay, good. Somebody finally typed something. Okay. All right. So Dan's is saying that maybe energy is not a physical thing. And Dan, that is exactly what they meant. Okay. So what they meant is that it's not something that you can hold in your hand. Okay. But I disagree when they say there's no such thing. I mean, that's like saying there's no such thing as love, right? You can't hold love in your hand, but that doesn't mean love isn't real. Okay, so they picked a poor choice of words here. So energy is very definitely real. It's just not something that you can hold in your hand. Okay, so let's talk more about energy. Energy is a word that you guys have used all your life. I'm sure. I'm sure late at night, you think to yourself, man, I just don't have any more energy. I better go to bed. Okay, or there are people who always try to sell you energy drinks. They say if you drink this, if you pay us money, that's the most important part. If you pay us money, then we'll give you this magic liquid where you drink it and it will give you energy. Yeah, what is energy? That's where the caffeine comes in. I got to that. So John stays up at night. Okay, and John is also saying that energy is neither created nor destroyed. Very important point. We will be talking about that in a minute. Okay, but what is this energy? This is a word that you guys have been using all your lives. But what is it? Okay, I need to see something typed in here. I need somebody to tell me, what do you think energy is? How would you define what energy is? ATP. Okay, you're going to have to elaborate on that one, Marshall. What do you mean? A type of impulse that can run things. It's in a biological sense. Energy is a force, something little children have. Yeah, boy, do they ever. Okay. All right. Okay. Well, tell you what. Let's go into it, and let's find out exactly what is this energy that you've been talking about all your lives. Oh, the ability to exert a force. Okay. Now we're starting to talk more like a physicist. So, Luke, I like the way you're thinking there. It's actually a little bit more than that, but what you say does incorporate a lot of it. Okay, so let's get into it. Okay, so question, what is energy? Well, if you look it up in the book or Google or whatever, okay, it's the ability to do work. So Sky is saying it's the potential to do something, okay, but more specifically, that something is work. Energy is defined as, this is the official physics definition. It is defined as the ability to do work. Okay, so if you don't have a lot of energy, you're saying, man, I'm just not able to do any work. I'm too weak. I'm too sleepy. So I pay somebody the money for their 5-hour energy drink, which is horribly overpriced, just a bunch of caffeine. But anyway, okay. And so then supposedly, if you believe the advertisements, after you drink the magic elixir, then you have the ability to go out and do all sorts of work. So great. So now we all know what energy is, right? Well, do we? Because what is work? Or, yeah, John is saying you have a heart attack, you drink too much caffeine. I agree with you on that, John. Okay, but anyway, if energy is the ability to do work, then the next follow-up question is, well, okay, but what is work? Because if you don't really know what work is, then you don't really know what energy is. Okay? So what is work? Okay, work is doing things. Okay, David, I like that, except that's a little vague. I mean, doing things. What kinds of things? Oh, okay, all right. So John, okay, John typed something. Let me read it. For those of you who are watching this not live but the recording, you unfortunately don't get to see the comments. So let me read word for word what John just wrote. He's saying, work in physics, measure of energy transfer that occurs when an object is moved over a distance by an external force, at least part of which is applied in the direction of displacement. Wow, I am impressed. Yes, yeah, I kind of guessed that. What John just typed in was he said he copied and pasted it. So yeah, I was pretty sure that's what you did. But you're absolutely right. Yeah, okay, so let's talk some more about work. Okay, so you guys, you know who Atlas is, right? He's one of the ancient titans, and it was his job to hold up the earth. Okay, so if it's his job, that means that's what he does for work. Okay, so imagine you are Atlas. Okay, so every morning, you wake up. Apparently, you don't shave. At least this guy doesn't. But you wash your face, you brush your teeth, and you go to work. You punch in at the time clock, and you hold the earth. And so for 8 hours every day, you hold the earth. Okay, and the earth is very, very heavy. So that's a difficult job you've got there. Only Atlas would be able to do it. Okay, so at the end of the day, that would not be a pleasant job. I agree with that. Okay, so after you've held the earth up here for 8 hours, you then hand it off to another Atlas who works the swing shift, and you punch out the time clock and you go home. So when you get home, your wife asks you, "Hey, honey, how was work today?" What are you going to say? Do you guys all agree that Atlas did a lot of work? I mean, his arms are definitely going to be tired. Okay. So Simon is saying that maybe Atlas didn't do a lot of work. John is saying that Atlas did do a lot of work. Simon, I'd like you to elaborate. Why did you say that you don't think that Atlas actually did any real work? If you want to turn on your microphone and speak your answer, that would be okay too. Just hold down the space bar.
Well, there's no gravity pulling the earth down towards whatever it is that he's standing on. So he's pretty much just doing a handstand for 8 hours. So it's not as much work as it's cut out to be.
Okay, I cannot argue with the truth of what you just said there. But let's suppose that we are ancient Greeks and we don't know that what you just said is true. Let's suppose that we do think that there is gravity there. And so he actually does have to do a lot of work. So if he really did have to push really hard, did he do a lot of work? Now, Sky is saying that he put a good amount of effort into it. I agree with you, Sky. But Sky, did he actually do any work? So tell you what, I won't make you guys guess anymore. Let me tell you, okay? According to physicists, okay, if nothing moved as a result of what you did, then no work was done. This is the official physics definition of work, is that in order for work to take place, you need to have pushed on some object, and that object has to have moved. Okay? If the universe didn't change as a result of what you did, then it doesn't matter how hard you pushed. It doesn't matter how much force you exerted. So Simon has come up with a number here for how much the Earth weighs. Okay, and that's a lot, right? So Atlas obviously pushed with a tremendous amount of force. But if the Earth did not move as a result of it, then he didn't do any work. Now, some of you are going to say, well, what he did was very important because had he not been holding it up, the Earth would have moved, it would have fallen down, and that would be bad. And I agree that that would be bad, but it doesn't matter. Okay, because think about it. If Atlas had been a little bit more clever, what he could have done is he could have just built a platform take a whole bunch of textbooks or a whole bunch of objects and stack them up there, and then just place the Earth on top of the platform, and then he could sit there for 8 hours a day reading a magazine. And what would the difference be, right? So the fact that you prevented the Earth from moving does not count. Well, the only thing that counts is if the Earth moved. Okay. Now John is asking, what if he spins it? Well, if he spins it, okay, then he caused it to move. And spinning force is something we are going to talk about later. Okay, but let's not go in that direction right now. Okay, so hopefully everybody agrees now that in order to do work, there are two things that have to be present. One, you have to exert a force. If the thing moves all by itself, then that doesn't count. You have to exert a force, and the thing that you're pushing has to actually move. Otherwise, no work is done. Okay, and in fact, here's an equation that you guys you had better write down, because you never know. You might see this equation on a quiz in a few minutes, and you will certainly be using this equation later as we go on. So work is defined as the amount of force that you're exerting multiplied by the distance that the thing moves as a result of you exerting that force. Give me a sec to read Sky's comment here. Assuming that the Earth did experience a force to cause it to move down, that he is then expending energy to oppose. Well, okay, so Sky, I like the fact that he is opposing the motion of the Earth, but he could have just built a platform and set the Earth on the platform, and no energy would have been exerted. Okay. Okay, so Danny is saying, isn't that weird? T equals F. Okay, Danny, I'm glad you picked up on that. Very, very good. You're very observant. Yes, we have two equations that look very similar. So Danny is saying that, hey, wait a minute, last time when we talked about torque, we said that torque was equal to force times distance. Now we're saying the work equals force times distance. What gives? Good catch, Danny. Okay, so here, I should have prepared a slide for this. So I'm just going to have to verbally say it. So pay close attention to what I say. I don't have a nice visual to go along with this. When we're talking about work, we are talking about the distance that the object moved. When we talk about torque, we are not talking about the distance that the thing moved. We are talking about the distance from the pivot point to the place where you're pushing. Okay, so even if the wrench that you're pushing on does not move, you're still exerting a torque. Okay, so the big thing here is the distance. So if you're talking about the distance that the thing moved, that's work. If instead you're talking about the distance from the pivot point to the place where you're applying the force, okay, then that's torque. So be careful about that. And Danny, I'm glad that you brought that up. And I'm impressed that you caught that. That's good. Okay, so now we know the official definition of work. Okay, so here's a little example. Kind of like you might see in today's quiz, wink, wink, nudge, nudge. Okay, so we got a horse here, and the horse is pulling the cart. And horses are pretty strong. They can easily exert 500 pounds of force. A human being would have a little trouble with that. There are some weightlifters who could probably do it, but a horse could easily do it. Okay, so the horse is pulling on this cart, and 500 pounds of force. And as a result of the force that the horse is exerting, the cart has moved a distance of 4 feet. Okay, so then how much work did the horse do? Well, force times distance, 500 times 4 is 2,000. And the units work out to be pound feet, or if you wanted, you could also say foot pounds. Those are interchanged. And again, you're going to say, hey, wait a minute, foot pounds was the definition of torque, or at least that was the units we use for torque. What gives? Okay. And I agree that this is potentially confusing. And so not only do I agree, but here is a case, one of the very rare cases, where even here in America, where we're stuck with this stupid imperial system, even here in America, people don't like talking about energy as being, or I'm sorry, work as being measured in foot-pounds because it is confusing. And so here's a case where even in America, when we're talking about work, it's actually more common to use the metric system when we're talking about energy. So John is saying that Americans see the metric system as communism. Well, there are certainly some people in America that do, especially Fox News. Tell you what I'm going to do. I'm going to post a link later to a video clip that I got where a Fox News consultant literally did say that the metric system is the work of those darn commie foreigners trying to force their system on us. It's hilariously stupid. Fox. I hope you guys don't mind if I diss on Fox News, but man, they deserve it. They say some of the stupidest things that you have ever seen in your life. Okay, but anyway. Okay, so even in America, it's very unusual to use this. So when you're talking about work, it's much more common to use the metric system. Okay, I'm not gonna bother to read all these comments. There's been a whole flurry of very interesting comments about the French and their involvement with the metric system. I'm gonna just kind of let those slide. Okay, so this is the way that it's more commonly done even in America. So when we exert a force, okay, let's say that we exert 500 newtons of force. Now remember, a newton is actually about a quarter of a pound. Marshall especially, Marshall, I hope you remember that. A newton is approximately a quarter of a pound. So 500 newtons is about 1/4 of what that horse was doing. And 500 newtons is something that a human being could easily do. Okay, and so we exert this force, and as a result of it, this object moves 2 meters. So then the amount of work that we've done is 1,000 Newton meters. And again, because Newton meters is also the same unit that's used for torque, here, what scientists have done is they have introduced a new term, which is the same as a Newton meter, okay? But if you use this term that you see here, which is joules, okay? Joules is exclusively used for work and for energy. We're going to talk more about energy in a second, okay? So so instead of saying 1,000 Newton meters, which is potentially confusing, you might say, are you talking about work or are you talking about torque? If instead of saying 1,000 Newton meters, you say 1,000 joules, then there's no question, there's no confusion. Everybody knows you're talking about work or energy rather than torque. Is breaking wood a form of energy or work? Well, okay, so it requires work in order to break the wood because you do have to move, you do have to cause the wood to move in order to break it. So you're doing work. And so hold that question for just a second here, because there's a connection between work and energy that I want to talk about. So let me do it in the order that I think makes most sense. Okay, so what you see here is a question very much like you might see on today's quiz. So I might say we exerted amount of force for a certain distance, how much work was done. Or what I might do is I might tell you how much work was done and how far the thing moved, and I might ask you to calculate how much force was required. I hope you guys realize that with the equation W equals F times D, I can just pick any two at random and then ask you to calculate the third one. And you guys are good enough with algebra that you should be able to rearrange things as needed. Okay, so you be prepared. You'll see a question like this on today's quiz. Okay, but I do need to warn you that what we've just talked about, work equals force times distance, is not the whole truth. And in fact, a few minutes ago in the comment field, one of you typed in a comment relating to this. Direction matters because remember how force is a vector? Well, okay, here's a case where the direction of the force matters, okay? So in reality, the real equation is force times distance times this weird thing that some of you know and some of you realize is not weird, but others of you in your math class, you haven't yet learned about trigonometry. So sines and cosines and tangents and all that fun stuff, some of you haven't learned about that yet. But you, when your teacher talks about it, pay attention because it's really important. All right, so here's an example to try and help you understand what's going on here. Okay, so let's say that the person pushing the lawnmower, they're pushing in this direction. You see this arrow down here that says F. Okay, so that's the direction that he's pushing. But you'll notice that the lawnmower is not moving in that direction. The lawnmower is moving in a different direction. Okay, so because force is not a scalar, it's a vector, you can't just take force times distance. Okay, you have to find what is the angle in between the force and the displacement vector. That's what you call this arrow up here. That's the arrow that shows what distance it moves and what direction it moved. Displacement is a vector as well. So you got to find the angle in between them, and then you have to multiply it by this thing called a cosine, which some of you know what a cosine is, but some of you don't. Okay. So what I'm going to do, because I'm such a nice guy, is that in the quiz that I give you today or later on in coming days, I'm always going to make it easy. I'm going to always assume that the direction of the force and the direction of the displacement, the direction that the thing moves, I'm going to always assume that they are pointing in the same direction. So then you don't have to worry about the cosine thing, which many of you don't know what a cosine is, right? Okay, so if the force is pointing in the same direction that the displacement is, then you're just gonna, you can get away with using work equals force times distance, okay? But be aware that in the real world, they're quite often not pointing in the same direction. So when your math teacher tries to teach you about sines and cosines and tangents, pay attention. That is really important and you need to know it. Okay, all right, so now we understand more about work. And we've already defined that energy is the ability to do work. So, okay, there are different types of work, and your book talked about this. And I asked you guys if you had any questions about the reading, and nobody said anything. So I hope that means that you understood what the book said. But just to be safe, let's spend a little time talking about it. Okay, so in the book, they talked about two types of energy. They talked about potential energy and kinetic energy. Kinetic energy is the energy that something has just simply due to the fact that it's moving. Okay, so this car that you see up at the top, the intention of this drawing is that car is not moving; it's sitting still. Okay, the car down at the bottom, it has slid down the hill, so it is now moving. It has the ability to do work. This box that you see in front of the car, what I intended with that is that's a wooden box that is sitting in the road. Okay, so this car comes along, it hits the box. Is it not going to push the box for a ways? And okay, it's going to cause that box to move. When this moving car hits that box, it's going to push it and that box is going to move. Yeah, the box is probably going to break. And if the box is too heavy of a box, then yeah, it's going to damage the car, but let's not worry about that. Okay, so I hope it's obvious that a moving car has the ability to do work. It has the ability to, when it hits that box, it's going to exert a force on that box. That box is going to move as a result. Therefore, that car definitely has the ability to do work. So we call that kinetic energy. Now, this car up at the top here, it is not moving. So it doesn't have any kinetic energy. But it's up high on the hill. And if we allow it, if we give it just the tiniest bit of a push, so it starts rolling down the hill, then gravity is going to take it from there. And gravity is going to make this thing speed up and it's going to go faster and faster. And when it gets to the bottom of the hill, it's going to have some kinetic energy. Okay. So when it's up at the top here, even though it's not moving, it still has the ability to do work. Okay. Because of the fact that it's up on a hill. Okay, so Sky is saying the potential is like stored work. And yes, Sky, that's a great way to think about it. I like that. Okay, potential energy is very much like stored work. It has the ability to do work. All you have to do is just release that ability. Okay, so in the book, they talked about potential energy and kinetic energy. Okay, Now, some equations that they gave you in the book, which I hope you guys paid attention to, because you never know, you might need these equations in a few minutes when you take the quiz, wink, wink, nudge, nudge. Okay, so if you want to know how much potential energy an object has, okay, and notice that I've called it gravitational potential energy. And in about 2 minutes here, I'm going to explain why I stuck the gravitational in front of it. But for right now, just kind of hold off on it. Okay, so because a lot of times when people say potential energy, they just leave out the gravitational and everybody knows what they mean. But in a couple minutes, we're going to find out there are other kinds of potential energy. So if you want to know how much potential energy, how much gravitational potential energy a thing has, what you do is you take the mass, and here's a case where you definitely want to work in metric system. It gets really confusing if you try to do this in the imperial system. So we're going to take the mass as measured in kilograms. So how many kilograms of mass does this car have? We're going to multiply it by G, which G is a special number that tells you how fast, or it tells you how much acceleration something's going to have. If I take my calculator and I let go of it, it doesn't just sit still. It starts moving, and it speeds up. Okay, when I first let go of it and it starts falling, it's falling relatively slowly, and then it goes faster and faster and faster and faster and faster. Okay, so that number G is a measure of how quickly does it accelerate. Okay, if you're using the metric system, there's a number for G that you need to have memorized. And I'm willing to bet that some of you already know what that number is. Anybody want to type in what you think the number is if you measure the acceleration of an object using metric units? I'm sure somebody out there knows what that number is. 8.5, nice guess, but no. Okay, Luke, good. I knew somebody would do it. Okay, so 9.8 meters per second per second. Okay, so what that means is, okay, every second that goes by, this thing's gonna be moving 9.8 meters per second faster. So if it starts off at 0 and I let go of it, 1 second later, that thing's gonna be moving at 9.8 meters per second. But a second after that, it's gonna be moving another 9.8 on top of that. So it's gonna be moving at 19.6 meters per second. And then 1 second after that, it's going to be going another 9.8 meters per second. So every second that goes by, this thing's going to be, the speed of this thing is going to have increased by 9.8 meters per second. Write that number down and remember that. That's going to be really important. Okay, now if you're using the imperial system, it comes out to be different, but we're not going to use the imperial system. Okay, so we're going to take the mass of the car, we're going to multiply by 9.8, and then we're going to take whatever is the height of this hill. However high this hill is above the lower ground, okay, that will tell us how much energy is this car has, just due to the fact that it's sitting up at the top of the hill. Okay, now Sky is talking about terminal velocity, and Sky, you are exactly right, but let's not go there. That's a little confusing. Let's save that for when you take a physics class, and we'll talk about that. Okay, so for kinetic energy, the form here is 1/2 mv squared. And again, when you take physics, we'll tell you where that equation comes from. But for right now, just kind of trust us. So with this car down here that's moving, if I want to know how much energy it has, if I want to know how much work it has the ability to do, okay, I'll take the number 1/2 and I'll multiply it by however much mass that car has. And then I'll multiply it by however fast it's moving, and whatever its velocity is, squared. The v has squared. Now notice the m is not squared. It's only the v that's squared. So 1/2 times m times v squared. So I trust you guys have written these things down. You will need these two equations. You will be using these two equations a lot. Okay, now there are different types of potential energy. This car that has energy because of the fact that it's up on a high hill, okay, if we just call it potential energy, we're really being lazy, because there are other ways to store energy. In the spring here, if I take a spring and I push down on the spring here, that compressed spring has energy. It has the ability to do work. If I take that compressed spring and I put it next to this, to a block or something, and then I let it go, that spring can push the block and it'll move the block. So that spring has potential energy too. And so the way to calculate how much energy a spring has is not mgh. It's different. I'm not going to talk about it in this class. Wait till you take physics. We'll talk more about it in physics. But I just want you to be aware that there are different types of potential energy. So I recommend, let's not be lazy. If we see a car up on a hill, I mean, technically we could get away with just calling it potential energy, but what I'm going to do is I'm going to call it gravitational potential energy so that you don't get it confused with spring potential energy. And yet there is still yet another kind of energy. If you have a gallon of gasoline or a couple of gallons of gasoline, that gasoline, if you pour it in your car, that has the potential to make that car move. And so that gasoline has potential energy too. We call that chemical potential energy. And when you take when you take Coach Miller's chemistry class, he will teach you how to calculate the amount of potential energy that is in chemical. And I can see right now that I spelled chemical wrong. Okay, but remember, spelling errors don't count as weak points. Only math and physics errors count as weak points. Okay, so chemical, if you spell it right, potential energy there. Okay, so now a couple more things that I want to talk about. And so what I'm going to talk about right now is not from last night's homework assignment. This is from the rest of the chapter, the part that many of you maybe haven't read yet, although I hope a few of you read ahead. You know, it's always good to read ahead. Okay, so on page 29, they talk about losing energy, and then they start off by saying, well, you can't really lose energy, which is something one of you typed into the comment box a few minutes ago. Yeah, energy is never really lost. It just changes form. Okay, you can change from one form of energy into another form of energy. Okay, and yes, heat is one of those forms of energy. Good point there, Sky. Okay, so let's look at this picture here. Okay, so ignore the car down at the bottom. Just focus all your attention on the car at the top. It has potential energy. So if that car rolls down the hill, when it gets down to the bottom of the hill, it no longer has potential energy. But what has happened is that potential energy has been transformed into kinetic energy. And however much potential energy it had up here, that is the same amount of kinetic energy it's going to have. So if it had 100 joules of kinetic energy up here, or of potential. If it had 100 joules of potential energy up at the top here, when it rolls down to the bottom, it's going to have 100 joules of kinetic energy if you ignore friction, which we're going to talk about in just a minute. Okay, friction makes things a little more complicated. So in the ideal world where you don't have friction, then the amount of kinetic energy down here will be equal to potential energy up here. It just changed form is all that happened. Okay. All right. And so then when it gets down to the bottom, if I have a box sitting there, when it hits that box and it exerts a force on that box, okay, then if it started off with 100 joules of potential energy, when it gets down here, it has 100 joules of kinetic energy. Then when it pushes that box, okay, it can do 100 joules worth of work on that box. Okay. All right. So let's pause for a minute and let's do a few practice problems like you're going to see on today's quiz. Okay, so I want you guys to type in some answers here. So let's say that we have a car. It's got a mass of 1,000 kilograms, moving at 20 meters per second. Somebody, I hope you guys have calculators. So always bring calculators with you. Okay, always. So anybody want to tell us how much kinetic energy? Okay, so Sky is saying 200,000. Holy cow, that's a lot. Anybody want to second that motion? So yes, joules is the right amount. Anybody want to second that motion, or anybody want to argue with him? Okay, Luke seconds it. Okay, good. And I agree. Okay, so you did it right. So 200,000 joules of work, or 200,000 joules of energy. That is how much kinetic energy it has. So if it were to hit a box and push that box, it means it could do 200,000 joules of energy on that box. Okay, let's do another question like you might see on, oops, wait a minute. Oh, rats, I hate it. I forgot to, okay, I got them in the wrong order there. Okay, so you guys just saw the answer. Yeah, yeah, I hate it when that happens. Okay, let's pretend that we didn't see the answer there. Okay, Don's, yes, I will go over how to calculate it. Okay, so the question is, we have a car with a mass of 1,000 kilograms sitting on a hill that's 50 meters above the ground. So how did you calculate it? Well, remember the formula for gravitational potential energy. It's m times g times h. So we know m is 1,000. Now in the problem statement here, I didn't tell you what g is, but I'm trusting that you guys know that anywhere on Earth, g, the acceleration due to gravity, that's the little g stands for gravity, okay, it's always equal to 9.8 meters per second per second, okay? Um, I trust that you guys have that one written down, okay? So we're gonna take m times g times h. So so when I get out my calculator, I take 1,000 times 50 times 9.8. That's where I get the 490,000 joules. So Dance, does that answer your question? Okay, so these are questions like you're gonna see on the quiz today. I trust you guys will do well. Here's another question like you might see on the quiz today. Okay, so let's say that some student pushes on a box, and so 40 newtons. Okay, so that's basically the equivalent of the weight of 10 hamburgers, right? That's not very much. That's something a student could easily be able to push with. Okay, all right, so Danny is suggesting that she did 100 joules, 120 joules of work. David is agreeing with that. Okay, and yes, joules is the right unit, and that is in fact the number that I get as well. Okay, remember, work is equal to force times distance. So we know the magnitude of the force, we know the distance. Now, what I didn't say here is I didn't specifically say that she's pushing in the same direction that the thing is moving, okay? Because if she wasn't, if she was pushing at an angle, then it wouldn't be force times distance, it would be force times distance times the cosine of theta, okay? But in tonight's homework, and basically for the rest of the year, I'm going to keep it easy. I'm going to always assume that she's pushing in the same direction that it's moving. So we can get away with working with using force times distance. Okay. All right. Now, if it's a frictionless floor, okay, hopefully you guys agree this gets interesting. So I've got this box. Okay. So here's a box sitting on the floor. I push on the box and I do 120 joules worth of work on this box. Okay, and it's a frictionless floor. Think of it as an ice skating rink and even ice skating rinks actually have friction, but let's say it's a perfectly theoretical ice skating rink. So when I do 120 joules worth of work on this box is now moving. That means this box now has kinetic energy. How much kinetic energy is it going to have? 120. Exactly right. Good job. Yes. Okay. If I did 120 joules of work on it, then it is going to have 120 joules worth of kinetic energy. Okay. Very good. Assuming there's no friction. Now, friction messes things up. We're going to talk about friction in just a sec. Okay. In fact, let's do it right now. Okay. All right. So if the floor is not perfectly frictionless, so as soon as I stop pushing on it, at that brief instant in time, it has 120 joules of work, but it's eventually going to come to a stop because friction is going to stop it. So where did the energy go? And David is saying that it went into heat. And David, you are 100% correct. That's exactly what happens. Rub your hands together like this. Okay. Do you feel the warmth? I mean, immediately. You can feel the warmth immediately. Okay, so when something is sliding across the floor and it has friction, what's happening is that it's generating heat. And so that 120 joules worth of kinetic energy is being converted into thermal energy. Okay. All right. So next question. The girl, she did 120 joules worth of work on the box. Where did she get the energy to do that? Because something had to give her the energy. David, very good. Food, yes, that's exactly right. the food that she ate that morning, or whatever she had for breakfast, yeah, and water. Okay, yes, okay. Um, so yeah, whatever it was that she ate earlier that day, okay, that is like the gasoline in a car. The food in your stomach, okay, it gets converted into energy. So that's where you get your energy from, is from the food that you eat. Okay, just a couple more questions. Um, so let's say that the girl now, she does 120 joules of work, but this time she's not pushing it across the level floor. She's pushing it up a ramp. And let's start off by saying, let's keep things easy. Let's say it's a frictionless ramp. Okay. So she did 120 joules worth of work to push it up that ramp. Okay. So how much potential energy does the box have? Okay. Before she lets it slide down. Okay. Well, I hope at this point you guys can see the pattern here. Okay. If she did 120 joules worth of work to push it up the ramp, it now has 120 joules worth of potential energy. Okay. All right. Okay. So when she lets go of it, okay, so she did 120 joules of work pushing it up the ramp. She now lets go of it. Okay. So for a brief instant, it has 120 joules worth of potential energy. When it slides down the ramp, when it gets down the bottom of the ramp, how much kinetic energy is it going to have? 120 joules. Okay. So I hope you guys agree that when you take today's questions, my mic broke. That's weird. Is it back now? So I just turned it off. And, okay, so it's back on now. Okay, thank you. That's really weird. I didn't click anything. Thank you for telling me that. That's bad. Okay, so let me just restate what I said there. So when she pushes up the ramp, she does 120 joules of work. It now has 120 joules worth of potential energy. When it slides back down, okay, and when it gets to the bottom, it's now going to have 120 joules worth of kinetic energy. Okay, so hopefully that's all pretty straightforward. Okay, now, the last thing, at least I think this is the last thing, okay? What if it's not frictionless? Okay, well, okay, so when it slides down the ramp, okay, when it gets to the bottom of the ramp, it's not going to have 120 joules worth of energy anymore because some of that energy got lost into heat. Whenever you have friction, what friction does is it steals away some of your energy and it converts it into heat. Now, in this class, I'm not going to ask you to do the calculations for how much energy gets converted into heat. I'll save that for when you take my physics class. We'll learn how to do that in physics. Okay, does the material of the ramp affect the friction? Absolutely yes. Okay, but again, I don't want to go into the details here. Wait till you take my physics class, and we'll learn all about that in my physics class. Okay, so we've already talked about where the loss energy goes, so I can skip over that. Okay, so those are the types of questions you can expect to see on today's quiz. Remember, you have 2 days to take the quiz. You don't have to take it today, but you do have to take it before class on Friday. All right, so there's a few more pages in chapter 2, but I think we've adequately talked about them, so I'm not going to make that be an official reading assignment. Your homework for today is to start reading chapter 3. Chapter 3 talks about simple machines. Now, in our CAD project, the thing that we CADed was a machine, but it was not a simple machine. Okay, it's like this bicycle. Let's use this bicycle as an example. A bicycle is what we call a compound machine. It's a combination of a whole bunch of simple machines put together. And I don't want to go into too much detail. In fact, I basically don't even want to go into any detail right now because we're running out of time here. It's almost been an hour, and I like to keep these classes to less than an hour if possible. But basically, in chapter 3, you're going to learn about a bunch of simple machines. And the way you make a compound machine is you take a whole bunch of simple machines and put them together. So it's vitally important you understand about simple machines. Now, your junior high school science teacher should have already talked to you about simple machines. So much, if not most, of what you read in chapter 3 should be review. You guys remember in your junior high school science class learning about things like levers and inclined planes and wedges and pulleys and all those things? Those are simple machines. Okay, so for your homework tonight, I'd like you to start reading chapter 3. I do not expect you to read the entire thing by Friday. I am mean, but I'm not that mean. Okay, but I would like you to have read maybe the first half of the chapter. I think that's a reasonable expectation. Okay, and I'd like you to make notes as you're reading. If you have any questions, come to class with a list of questions that you can ask. And so, other than taking the daily quiz, which remember is a very important assignment, uh, other than that, there's not really any homework to do. Okay, so before I turn off the recording, let me just say, are there any questions? Okay, so no questions there. Okay, good. All right, so you know the routine here. So I'm going to say going once, going twice, sold. Okay.